In this video, we're going to take a look at two variations of the mixture problem that we did in the previous video. So if you haven't seen that problem, you might want to go back and watch the previous video. So just to remind you, the problem initially was the tank contains 1,000 gallons of water and 10 pounds of pollutant dissolved in there. We got water being dumped in, we got stuff being dumped out. Water's coming in at a rate of 0.2 pounds of pollutant per gallon and 5 gallons per minute, and the mixture is being dumped out at 5 gallons per minute. Okay, so what I want to do this time is I want to change that 0.2 pounds of pollutant to 0.002 pounds of pollutant per gallon. So the concentration initially here was 10 in 1,000, so that's 0.01 is the concentration in pounds per gallon. So to go to 0.002 is going to mean I'm dumping in a less concentration than what's already there. So I would expect the amount to be going down. So this is all the calculations from last time and the graph from last time, and now we're going to look at this variation. Okay, so the concentration coming in is 0.002. So the differential equation looks very much the same as before. It was the concentration coming in pounds per gallon times the rate that it's coming in at 5 gallons per minute. And then this was the concentration in the tank, Y pounds total divided by 1,000 gallons times the rate that it's going out at 5 gallons per minute. So the only difference from before is that this, in the previous example, was a 0.2 and now it's a 0.002. Which, of course, 0.002 times 5 is 0.01, and now I'm looking at this. So it's, again, a separable differential equation, or first-order linear. I'm choosing to do it as a separable equation. So dividing everything by that complete right-hand side, multiplying by dt, integrating, the calculations are very much the same. It's just that you got a 0.01 here rather than a 1. 0.01 there rather than a 1, 0.01 rather than a 1 from the previous example. Everything else is the same from the previous example. And now it looks a little bit different because when you add the point or subtract the 0.01 over the other side and then divide by that minus 0.05, what we get here is a 2. I think in the last one, what did we get? What did we get before? We had a 200. Well, okay, maybe that makes some sense that decimal place should be moved over 2. So yeah, we get a 2 there. Plugging in initial conditions at time 0, we still have 10 pounds of stuff. And C this time turns out to be 8. Right? So this now looks like a decaying exponential scaled by a factor of 8 and shifted up 2. So sure enough, it starts off at 10, and over time, the amount of stuff decreases. This has a horizontal asymptote of 2, which again makes some sense because, again, in reference to what I said in the previous video, because the amount of water in the tank is always 1,000 gallons, and we're pumping it in at a concentration of 0.002. So 1,000 gallons times 0.002 is 2. And so we would expect that over time we should be approaching that concentration of whatever the incoming solution is, 0.002. So that was what we get with a horizontal asymptote of 2. Okay, so there's my first variation. Now, second variation. Let's go back to the concentration is, again, 0.2, so we would expecting to be increasing the amount of pollutant in the tank. But I want to take water out faster than I'm putting it in, right? So I'm essentially emptying the tank at the same time. So there's going to be 5 gallons per minute coming in, but 6 gallons per minute going out. Okay, so since there was originally 1,000 gallons, I would think that I'm going to empty the tank in 1,000 minutes, right? Because each minute I'm going to lose a gallon. So let's take a look at how this differential equation looks. Again, Y is the number of pounds of pollutant in the tank. The rate of change in Y with respect to time, so dy dt, pounds per minute, is the rate coming in, pounds per gallon times gallons per minute. So 0.2 pounds per gallon, 5 gallons per minute, that's what's coming in, minus the concentration going out times the amount, the rate going out. So the thing is now, the concentration isn't just Y divided by 1,000. The thing is the volume of water in the tank is changing. Every minute I'm losing 1 gallon. So after T minutes, I've lost T gallons. And 1,000 minus T is the function that's telling me the volume at any time. Y is the function that's telling me the amount of pollutant, pounds of pollutant at any time. So there's the concentration at any time now, and then times 6. Did you notice those 5s just turned into 6? Yeah, I don't know why when I initially wrote this up I had 5s in there, but the outgoing rate is 6 gallons per minute. So, so here's the concentration going out at a rate of 6 gallons per minute. So that's the total amount of flow going out, the rate of flow going out. So, simplifying some things here, there's my differential equation. Now with the presence of this T down here, this is no longer a separable differential equation. It is, however, still first order linear. So if I take this and move it over to the other side with a plus sign now, this is of the form that we want. 1 times dy dt plus p of t times y equals g of t. Okay, so the integrating factor is going to be e to the integral of this thing. So here we go. The integrating factor is e to the integral of that stuff, which I think I do correctly here. Yes, there is a U-substitution with u as the denominator here, so du is minus dt, hence the minus sign showing up there. And then I got a natural log of 100 minus t. This simplifies because the minus 6 can come in as an exponent, and e to the log of this thing to the minus 6 is just this thing to the minus 6. So there's my integrating factor. If I multiply both sides of this thing by that integrating factor, then the left-hand side is the derivative of the product of y and the integrating factor. And when I integrate that derivative, I get y times the integrating factor. On the right-hand side, I multiply this by the integrating factor and integrate that. So then I integrate this thing to get the stuff in parentheses. Notice the plus c is in there because this thing will be multiplied by or divided by, whichever way you think of it. But with this to the negative 6, I'm multiplying both sides by that thing to the plus 6. And the integral here, I do a U-substitution with u equal the stuff in parentheses. So du is minus dt, and then I end up with a negative u to the negative 6 du, and so there's a negative, and it integrates to this thing to the minus 5 divided by minus 5, so the two minuses cancel out, and then I distribute this thing in, and so this thing times that, so the plus 6 and the minus 5, it ends up being just to the plus 1 power, and then this times the c is this. I will admit that as a student, I had a tendency not to put the plus c in parentheses because that integral, the plus c is part of that integral, and then it gets multiplied by this stuff. So I would end up with just a plus c over here, not times this thing. And it's like, wow, I just get a linear function? It's like, how does that work? I just wouldn't expect it to be linear. And so it's like, why? Why was it linear? Well, it's not linear because I didn't do it right. So anyway, the plus c goes in the parentheses and then gets multiplied there. Initial condition. I can plug in at time 0. I have 10. So the 0 goes in there and it goes in there. And I end up calculating that c equals minus 1.9. Oh, this is a weird way to write it. That's not supposed to be an x. That's 1.9 times 10 to the minus 16. I was trying to do, what do you call it? Scientific notation. Anyway, that's 1.9 times, minus 1.9 times 10 to the negative 16. Plugging that in, again, it looks funny there, but there it is, the formula. The graph of this thing now looks like this. which is interesting because as in the very first example in the previous video, the concentration coming in is more than the concentration I started with. So I'd expect the amount of pollutant to be increasing. But then eventually, since I'm pumping everything out faster than I'm pumping it in, I'm losing a gallon per minute, that in 1,000 minutes, the whole thing is going to be, the whole tank is going to be empty, so there isn't going to be anything in it, and then the whole model breaks down at that point. But see, this is what I see, that initially I'm getting more and more concentration. But then it starts going down because the total amount of water is down, and so even at a high concentration, the amount of stuff is less. And you can see that it builds up to some maximum amount and then empties out again. Okay, and right there at 1,000 is where the tank is empty and there's no pollutant in the tank because there's nothing in the tank. Okay. So anyway, there's a couple of variations just to show you some of the things you might run into as you're working problems out of the textbook. So